Hello students. Today's topic is an indeterminate structure. Basically, we'll discuss the method of analysis for the propped cantilever beam, as well as we'll discuss the method of analyzing and finding out the deflection, bending moment, shear force in case of a fixed beam. So let's start. It is in continuation with the previous lecture, in which we have studied some of the basic methods for analysis. Example, unit load method, consistent deformation method, and slope deflection method. So in this method, we will be studying the some other methods of analysis for the indeterminate structure. Myself, Shubhranshu Jaiswal, Assistant Professor, BCE University, Lucknow. Now, in order to start the analysis, we need to remember a few equations. This is very basic equation that says moment is that says E V double dash, that is a double integration is equals to the moment, EI V triple dash, that is a triple integration, that is equals to the shear force, and the fourth integration is equals to the load itself. So we'll see this by using an example. First of all, this is a basic example for a propped cantilever beam. And this question we are concerned to determine the reaction, shear forces, bending moment, slope, and deflection for this propped cantilever beam. This propped cantilever beam is having one end fixed at A, other end is roller at B. The beam is carrying a UDL of intensity Q throughout the beam. The number of internal reactions that will act in this case will be this MA, this is a rotation that will be due to the fixed support. This vertical reaction RA due to the support condition, as well as this vertical reaction RB due to the support condition at B. So let us start. We'll start analyzing this beam by using equilibrium condition. The first equilibrium condition says sigma V is equals to 0. That is, sum of all the vertical forces should be equals to 0. So it says RA plus RB is equals to QL. So this equation turns out to be like this. This says RA plus RB is equals to QL. So RB goes into that side, and the equation becomes RA is equals to QL minus RB. Now the other equation says the sigma M at any point should be equals to 0. So sum of all the force moments towards any point should become equals to 0. This is a second equilibrium condition. So let us take moment about moment about B, and say it is equals to 0. So sum of all the moments about B will be, first moment will be this MA, this moment will be MA, second moment will be this QL. This QL is the force, and the perpendicular distance will be L by 2. So this becomes QL square by 2. And the third is this. We can say this. Okay, so let's not take about B. Let's take about A. Let's take about A. So what will be the moment about A? It will be first will be this MA. It is already a moment, so it will not be multiplied by any perpendicular distance. Second is this QL. This QL is the load, and the perpendicular distance will be L by 2. So total load, this moment will be QL square by 2. Third is this RB. RB into perpendicular distance. This is RB multiplied by L. So this will be RBL. So this equation turns out to be like this. It says MA is equals to QL square by 2 minus RBL. And if everything goes to this side, the equation becomes 0. That is a sigma MA is equals to, sigma MA is equals to 0. So now if we calculate a simple moment about any section XX at a distance x from the end A, the equation will be like this. This says mx, this is the moment on any section. This is mx is equals to RA multiplied by x. This is the x, the distance from the section, minus ma will be as it is because it is a moment, not a load, so it will not be multiplied by any perpendicular distance, minus ma minus qx square by 2 due to this load udl q. Solving this will be, we can simply put the value of ra from here to into this, and we can get the modify this equation to be like this, and simply we have substituted the value of na from this equation to this equation, and we can get the moment equation, moment about at any section x to be like this. And if we proceed further, this says we can simply use this equation. This says m is equals to ei v double dash. So we have calculated m over here, and we know this relation, that is m is equals to ei v double dash. We'll simply put the value of m over here, and we'll solve the equation for the value this. So it will be like this: v ei v double dash will be is equals to m, and the value of m that we have calculated over here, sorry, that we have calculated over here, we'll substitute this value to this equation. Similarly, if we integrate this equation, if we again integrate this equation, this will be ei v dash, and the equation will become like this. This is a ql x square. On integrating x, we'll get x square by 2, so it will be ql x square by 2 minus rbx square by 2 minus ql square by 2 x minus rblx minus qx cube by 6 plus c1. This will be plus c1. This will be as it is because there was no x over there, so it will be x. X will come to this side, and the c1 is constant due to the integration. Then again, on integrating this equation, we'll simply get qlx cube by 6 minus rbx cube by 6 minus ql square x square by 4 minus rblx square by 2 minus qx4 by 24 plus c1x plus c2. Now, if we apply boundary condition to the calculated integration equations, the boundary condition obviously says v0 is equals to 0, okay, v naught v dash 0 is equals to 0, and vl is equals to 0. So by applying boundary condition to this equation, we both of the equation, the value of c1 and c2 can be calculated to be 0. Then by putting this value in that equation, the value of rb comes out to be 3ql by 8. Value of ra comes out to be 5ql by 8. The value of ma comes out to be ql square by 8. So these are the final reaction and moment values that we were concerned with. We were not known to neither ra nor rb nor ma. So we have finally calculated these things. Now, next we will calculate the shear force. So the shear force and bending moment about any section. This is V is the shear force at any section. That is simply shear force at any section will be Ra minus Qx. Ra will be due to this, and Qx will be due to this UDL. So Ra minus Qx, we have already calculated Ra. We'll substitute the value of Ra from this equation to this equation, and this will become 5QL upon 8 minus Qx. Now, similarly, moment again will be Rax minus Ma minus Qx square by 2. Similarly, we'll put the value of Ra in this equation, and we have already calculated Ma. So we'll put both of the values in this equation, and this will be our the equation for the final moment and final shear force. Now, the maximum shear force, if we plot a bending moment diagram for this. If we calculate, if we plot a shear force diagram for it, it will be like this. We have not, okay. So we have already calculated the shear force. So let us plot a bending moment diagram for it. So bending moment diagram will be like this. This portion is a positive moment, and this portion is giving a negative moment. So when we talk about the positive moment, the highest peak is this point, and over here the highest positive moment is 9q L square by 128. And when we talk about the negative moment, this is the highest peak, and this gives the value of QL square by 8. So the maximum shear force will be 5QL by 8, and obviously this is the maximum shear force. If we see here, the maximum shear force will be at the fixed end, and that is equals to Ra, and the value of Ra is 5QL by 8. So maximum shear force will be equals to 5QL by 8 that we have written over here at the fixed end. Similarly, the maximum positive bending moment is this 9QL square by 128, and the maximum negative is minus QL square by 8. Now in this way we have calculated the maximum positive and maximum negative bending moments also. We have calculated the maximum shear force in this case. We have already calculated the unknowns, that was Ra, the Ma, also the Rb. So now we need to calculate the slope and deflections also in this case. Basically, by calculating all these things, the analysis procedure will be completed. So what is analysis procedure consists of finding out the reactions or unknowns that has been asked during the analysis process. Also, if required, we need to draw the final bending moment and shear force diagram in order to clearly represent the values which we have calculated, and show the variation from one end to other. So in this way, we'll calculate now the slope and deflection of this beam. So V dash is equals to, this equation gives the slope equation, and by integrating it again, this will give a deflection equation. So this equation is for slope and this equation is for deflection. We'll simply apply the boundary conditions and calculate the slope and deflection, final slope and deflection at any point. So to determine the maximum slope, for maximum slope, we know V dash is equals to 0. So simply in this case, we will put the value of V dash is equals to 0, and we'll calculate the maximum slope. The equation turns out to be like this. This is, on putting V dash is equals to 0, this portion will become 0, and this portion will become is equals to 0. So minus 6L square plus 15LX minus 8X square is equals to 0. This is equation for the maximum deflection. So we know that x1 is equals to 0.5785 L. So we'll put the value over here, and the equation for Vx1 turns out to be like this. So this is the for condition for the maximum, because we know that maximum will occur at. So in this way, we can calculate by the slope deflection by using this equation. We can see that we have already seen that this equation will give at x1 is equals to this value. This is a maximum value. It will give the delta max is equals to like this. Then again, for the variation point, if when m is equals to 0, then x will be is equals to L by 4. The slope over there will be theta b, and it will be y dash at x is equals to L. It will be q upon 48 EI in this equation. So we can, by using the two of the equation, at x is equals to any point. For example, we say at x is equals to 1. This equation will give the value of slope, and this equation will give the value of deflection. Similarly, by for any value of x, we can simply calculate the deflection and slope using the two of the equation. So in this way, we can simply calculate all the reactions, shear forces, bending moments, and the unknowns we have already calculated. In this case, we were concerned with the reactions, and we have calculated RA, RB, We have a concern with the shear force, bending moment. We have calculated. We were concerned with the slope and deflection. We have calculated. So in this way, we can do the analysis of prof cantilever beam. Whatever parameters we are asked for, we can easily calculate using this method. Now let us see one example of a fixed beam. In this case, this is a fixed beam. Both end A and end B are fixed. This fixed beam is carrying a concentrated load P at the mid span. The span is of L. Again, same over here also we need to calculate the reaction, shear forces, bending moments, slopes and deflection. So in this case, we can clearly see that there will be three forces at each end. One will be vertical, other will be horizontal, and third one will be the moment. So this is a vertical force RA. The horizontal force will be HA over here and HB over here. We can clearly see that HA will cancel out HB because the load is acting in the mid span. So we can simply say HA is equals to HB is equals to 0. MA is the moment due to this fixed end. Also MB, the moment due to this fixed end. So by using first equilibrium equation, that is sigma of V is equals to 0, we can say RA plus RB is equals to P. RA plus RB is equals to P. So we can simply say due to symmetry, it gives RA is equals to RB is equals to P by 2 due to the symmetry. This load will be distributed equally to each end. And we can clearly write down, directly write down RA is equals to RB is equals to P by 2. Similarly, MA will be equals to MB in this case because this is a symmetrical beam. So MA will also be is equals to MB. Now we need to calculate a moment about any section, say X, and whose distance is X from the end A. So moment will be on the section will be Px by 2 minus Ma. Px by 2, this is P multiplied by X by 2 minus Ma. Ma is the moment, and this will be from 0 to L by 2. This is into this region. This is into this region. This is 0 to L by 2. Now, when we talk about 0 for this span, it will be Px by 2 minus Ma for 0 to L by 2. For the same thing, we will be putting this equation, that is EI V double dash, and we know this equation, that is EI V double dash is equals to M. So we'll simply calculate over here. Again, after integrating in the same way we have done in the case of a prop cantilever beam, EI V dash is equals to Px square by 4. This equation we have integrated it, Px square by 4 minus Max plus C1. Again, integrating it, we'll get Px cube by 12 minus Max square by 2 plus C1x plus C2. This is within the limit of 0 to L by 2. This is within the limit of 0 to L by 2 for one section. Then again, applying the boundary conditions, V0 is equals to 0 and V dash 0 will also be equals to 0 because it is a symmetrical condition. So V dash 0 will be equals to 0. Here are the final forces. This PL by 8, PL by 8. This is MA, this is MB, this P by 2 is the RA and RB due to this load P. So in order to calculate the C1 and C2. So this is how we can calculate the value of V dash and V at any point using both the equations. We can see the C1 and C2 can be calculated in this way. C1 is equals to C2 is equals to 0. But we have been calculating it using the both of these equations by applying the boundary conditions. So I'm putting the value of C1 and C2. The final MA will be equals to PL by 8, and this will be similar to the equal to the MB because due to the symmetry, this MA will be equal to the MB. Now we can clearly see this the bending moment for this thing. It is PL by 8 maximum over here, and PL by 8 maximum negative over here. This portion is giving the maximum positive bending moment, and this portion is giving the maximum negative bending moment. So maximum positive bending moment will be this one, sorry, this one, and maximum negative will be this one. So due to symmetry, we can easily see the plot is also symmetrical. It is the varies from this point to this point in a linear way, also from this point to this point in a very linear way, and the graph area is symmetric at both the parts. So the shear force and bending moment diagrams are this. This is a bending moment diagram. Now we need to calculate slope and deflection in the similar way we have calculated in the case of a propped cantilever beam. So in this way, v dash becomes equals to this is the equation for slope again. That is minus px upon ati L minus 2x for 0 to L by 2. Again, on integrating this thing, we'll get minus px square upon 40 adi 3L minus 4x. This is again as in the previous case we have seen, this is a slope equation and this is a deflection equation. So on putting various values of x in slope as well as deflection equation, we can easily calculate both slope and deflection for the further cases. Now maximum deflection, that is del max, is equals to minus will be occur at L by 2. This is the maximum deflection that will occur at L by 2. We can easily see on applying this force is acting on a length L by 2. So when the deformation of this beam will occur, the deformation shape will be like this. You can easily see if the deformation of this beam occur, because deformation and deflection of end support will be 0, deflection of end support B will be 0. So obviously because there is a fix at both ends, so it will not be able to deflect from the ends. So on the application of downward load B at the mid span, the deflection curve for this beam will be somewhere like this, and this will be the maximum deflection, and this the maximum deflection will occur under load, and the load is acting at a distance L by 2. So we can clearly see that del max will be at L by 2. So we can clearly see in this case also the del max will be maximum at the center because the ends are fixed, so they will not be able to deform. Though the certain rotation will be there. So rotation we can clearly see if this is a rotation, this is theta A, this is a rotation, this is say theta B, whereas this is a deflection, we can say delta C or delta max, because the maximum deflection is occurring on the center itself. So this is how we can clearly see how we can find out where the maximum deflection occurs. In this case, it is at the center. So we have easily calculated. Now, in this way, delta max will be at center, and on putting the value of L by 2 over here, it will give P L cube by 3. In place of x, we will be putting the value L by 2. So on putting the value, V dash will be this is V dash will be equals to PL cube upon 192 EI, and this is a maximum deflection. That is sorry, in this case, because this is a slope equation and this is a deflection equation. So deflection, on putting the value of L by 2 in the deflection equation, we'll get simply a deflection at L by 2, and we know the maximum deflection occurs at a distance L by 2 from each end. So this will become PL cube upon 192 EI. Similarly, the point of inflection occurs at the point where m is equals to 0. Obviously, the point where m is equals to 0, the point of inflection. So point of inflection will be where the moment is 0. So moment is 0 at the center. So it will be at L by 2. So we can see the point of inflection is uh, moment is 0. That is at x is equals to L by 4. The deflection is okay. So moment is 0, and x is equals to L by 4. We need to calculate the point of inflection over here. That is at L by 4. So at L by 4 again, instead of this value L by 2, we'll put the as x is equals to L by 4, and at x is equals to L by 4, it will be PL cube upon 384 EI, and which is equals to del max by 2, because obviously we can see the variation is linear from this end to this end, and the deflection at this part will be just half of the deflection at the center part, and also the deflection at this part will be half of the deflection at the center part, and it goes to a negligible amount, or we can simply say 0 to the end A as well as end B. So in this way we can clearly see that we have calculated the deflections, also the slope for a fixed beam also. Remember one thing we need to see also in this case, as well as in the case of a prop cantilever beams, uh, when we calculate the shear forces, also the bending moments, we need to calculate the reactions first, because when all the reactions are known to us. Similarly, in this case, as we can see, this is a basically indeterminate beam. So in this indeterminate beam, there are three support reactions over here. There are three support reactions over here. Uh, Three support reactions are over here. So the basic indeterminacy of in this case is three. We can clearly see at this end, the number of internal reactions are three. Also at this end, the number of internal reactions are three. So we just need to calculate it like this. Total number of reactions are six, and 6 minus the equilibrium conditions, and equilibrium condition for 2D frame is 3. So total number of indeterminacy in this case is 3. So basically we can clearly see that three extra equations are there. Hence we need to calculate the unknowns, and in this case unknown is HA, HP, also this MA and MB. So in order to calculate the unknowns, we need to do this procedure in which we can clearly see if this and this case was a case of a symmetrical beam. Also, if this case was of a unsymmetrical beam, we can clearly see like this. Uh, Due to symmetry, this all things happens. Due to symmetry, this thing happens like this. Just a second. Due to symmetry, this HA was equals to HB. Also, this MA was equals to MB. But if the case wasn't like this, if this would have been a case, this load P was acting like this end was fixed, also this end was fixed, then uh, it, this distance would have been say A, and this would have been B. Then in this case, this MA will not be equals to MB, because moment at this part will be different as the moment in this part. So also the HA will not be equals to HB. So this was a case of a symmetrical beam, but in case of unsymmetrical beam, the condition will not be like this. So in those cases, we need to solve this equation more precisely in order to calculate all the unknowns reaction, and we'll discuss the procedure in a very descriptive way in the upcoming lectures, where we will be dealing with the more specific methods of finding deflection, for example slope deflection method, for example moment distribution method, uh, matrix method of analysis of a structure. We'll be dealing in more precise way for the analysis of more complex beam and frames. So in the upcoming lectures, we will be dealing with the specific methods of analysis of an indeterminate structure. This was a basic understanding about how we analyze a structure. What does analysis means? What parts are included in the analysis of a structure? So till then, thank you, class. Thank you.